So one of the first topics in 2.1 is finding the average velocity of an object moving along a line given by a function's formula. An average velocity is just another way to say the slope. Now the line we're finding the slope of is called the secant line because it connects 2 points that lie on a different graph with a straight line. So in this example we want to find the average velocity of s sub t, which is t squared minus 1, on the interval 1 to 4. When they give you an interval, that's always the independent variable. So in this case it's t, because that's what the x-axis is being replaced by. And the y-axis is being replaced by s sub t. So a lot of times they'll write s. So we're plugging into the slope formula, y2 minus y1 equals x2 minus x1. But in this case the s is like the y and the t is like the x. So our slope formula has s sub 2 minus s sub 1 over t sub 2 minus t sub 1. They've given me the two t values. I know the first t is 1 and the second t is 4. So I can plug them into my function to figure out the s values, which are like the y values, and then I'll find the slope, which is the average velocity. Here's a picture of the actual line we're finding the slope between. And that red line is called the secant line, or a secant line. So, first I'm going to plug in 1 for t, and I get 1 squared minus 1, which gives me 0. And I plug in 4 for t, and I get 4 squared minus 1, which is 15. So my s sub 1 is my first t, and my s sub 4 is my second s at my second t, so that's like my s sub 2. So to find my slope, I have s2, which is 15, minus s1, which is 0, over t2, which is 4, minus t1, which is 1. And this is 15 over 3, which is 5. So the slope of the secant line, sometimes they write m with a little s, is 5. And that looks like a line that has a slope of about 5. So if we want to find the slope of the line at a single place, for example, just at t equals 1, we can get closer and closer to what that slope would be as the secant line gets closer and closer. The second point on the secant line gets closer and closer to 1 in this case. So we're going to do from 1 to 3 in the next example, and from 1 to 2. And we're going to look at what happens to the secant line, which is the red line in this example. So we're going to do the same thing again. We're going to find the average velocity. But this time, instead of going from 1 to 4, we're going to go from 1 to 3. And it's the same equation. S sub t is t squared minus 1. So the same formula holds. I plug in 3 for t. I need to get the y values. I plug in 3 for t. I get 3 squared minus 1, which is 8. And I plug in 1 for t. And I get 1 squared minus 1, which is 0 again. So now when I find the slope of the secant line, it's my second t value minus my first t value. That's the second one because it comes from my second t. And this is my first one because it comes from my first t. So it's 8 minus 0 over 3 minus 1, which is 8 over 2, which is 4. Well, notice the slope of the secant line is getting smaller. So we'll do this example again, except this time we'll go from 1 to 2. So this time it's the average velocity, just like before. And just to recall, the average velocity is the slope formula. In this case, my s's are like my y's, and my t's are like my x's. And we call this the secant line, that's what the little s stands for. And in this case, I'm going from 1 to 2. And those are my t values, my independent variables. So I have to plug in 2 into t squared minus 1, because that's the equation of this line still. And I get 3. I plug in 1, just like the other 2 times. I get 0. So the slope of the secant line is 3 minus 0 over 2 minus 1, which is 3. Well, notice it's gone from 5 to 4 to 3. And ideally, what we're looking to do is find the equation of the secant line at just t equals 1. And if you look at that very closely, same equation. I would like to find the equation of the line. It just touches the graph at 1. We've been getting closer and closer to this. Now this line's called the tangent line. The tangent line to t squared minus 1 at t equals 1. But the problem with finding the slope here is there's only one point on this line that touches the graph, namely at t equals 1. So we can't get the slope of that line because we need 2 points to plug into the slope formula. Remember, the slope of the secant line is s2 minus s1 over t2 minus t1. And then I have to give you 2 points that lie on that line. That's what we've been doing so far. Well, the problem is there's only 1 point here. So we make up a second point to come up with the equation of the tangent line. And this is called the instantaneous velocity. And to do the instantaneous velocity, we have to use something called a limit. So first let me set it up. The trick is we need to pick a point very, very close to 1, and over to the right a little bit. So I'll have 2 points to plug into this formula. The problem is I can't think of the smallest number. What if I only move 0.1 over? Well, I could have moved 0.01 or 0.001. And you'll notice the closer I get from my second point to being at 1, the closer and closer the secant lines turn in to the tangent line. So the trick is they use a second point, which they call t plus h. In this case, it'll be 1 plus h. And h is the step I take over to the right to get to the next point. And on the graph, there's another point that would be here that I could find the secant line between. Now I'm going to make the secant line blue in this case. And the trick is, the closer and closer I make, the smaller I make h, the closer those 2 points lie together. If I could make h equal to 0, I just have a single point there. Well, so that's what I'm going to do. I'm going to let my second point, my first point be 1, but now my second point is going to be 1 plus h. Now I've got to figure out the y value. When I plug in 1 plus h, that means I replace every t with a 1 plus h. And when I plug in 1, I get 0 again, just like before. Well, I can expand this out. Remember, you have to FOIL. A lot of people forget to FOIL here, just because it's easy to forget when you're thinking about other stuff. But this is one that will show up a lot. And when you FOIL that, you get 2h plus h squared, and then there's that minus 1. So this becomes 2h plus h squared. So now I can find the slope of the secant line, which is s2, that's the 2h plus h squared stuff we just found, minus s1, which is 0. My t2 was 1 plus h, minus my t1 is 1. And what I get is 2h plus h squared over h. That's the equation of the secant line. But ideally, I wanted h to be 0. If h was 0, then the 1 plus h would be 1 plus 0, which is just 1. And there'd be only 1 point on my line, which would give me the equation of the tangent line. Well, this is where calculus comes in. All calculus is a limit. And a limit is getting closer and closer to what you'd like to plug in. I'd like to plug in h equals 0, but I can't, because there's an h in the denominator. So in calculus, we use the limit as h approaches 0. So this means you don't have to plug in 0 for h, you just want to get close to 0. Now I'd like to plug in 0 for h, but right now I can't because h is in the bottom. But if we work this out, and the nice thing about math is, and you'll see later, that these all work out to give us derivatives, and when we work these out carefully, it'll always happen that you can cancel the h out of the bottom. Well, at least for the ones we'll be doing. Using one technique or another. And this is one of the more straightforward techniques, where the h just cancels by factoring. But this magical thing that happened is not a coincidence, and it happens quite often. You can cancel the h out of the bottom when you take this limit. You let h get smaller and smaller. And after you cancel the h out of the bottom, you can actually plug in, and you get the limit equals 2. But what that limit did was it let h be 0. But when h equals 0, then we really only had one point on the line. Remember, we were going from 1 to 1 plus h. But when h equals 0, this becomes 1 to 1, or just at t equals 1. So what we've done is we've taken the limit as h goes to 0 of s of t, s of t plus h, because that's what we plugged in, t plus h, minus s of 1 this was 1 plus h over h, and this gave us our tangent line slope. Which is called the instantaneous velocity. So the average velocity is how far you've gone distance over how long it took you time. The instantaneous velocity is the velocity at a specific moment. In this case, exactly when the time is 1, the velocity of this particle is 2. And this tangent line is a way that we can generalize an instantaneous velocity. So in general, if you're trying to find an instantaneous velocity, this has to do with something called the derivative. It really comes from the average velocity. You just let an h go to 0. So in general, to find the tangent line equation, which is the instantaneous velocity, it's just the slope of the tangent line, which is the line that just touches at a single point. Instantaneous velocity. And this is the limit as h goes to 0 of s of t plus h minus s of t over h. And this is the formula that lets you find the instantaneous velocity for any function. So we'll do a quick example, and then we'll show how we can do this with tables and graphs as well. So consider the graph we were looking at, which is s of t equals t squared minus 1. We were looking at when t was equal to 1, and we found the equation of the tangent line at t equals 1. But we can, or the slope of the tangent line at t equals 1. But we can actually come up with an equation. So instead of just finding the tangent line at t equals 1, the slope of the tangent line at t equals 2, we can get a general equation for the slope of the tangent line. And then you tell me where to look, and I'll plug it into my general equation, and it'll tell me the slope at that point. And the way we do it is we let our starting point be t, and then our ending point will be t plus h. So this means we don't necessarily have to start at 1. We're starting at a general point, which we're calling t. And when I plug t into my value, I get a y value, which we call s of t. And I'm going to do the same trick. I'm going to take a baby step over, which I call h. I want h to be as small as possible. Ideally, it would be 0. When I plug in that point, I get s of t plus h. So to find the slope of the tangent line, I just have to take the limit as h goes to 0 of the second point minus the first point over. Well, here's where the h comes up. There's the second t plus h, minus the first t, which is t. And so you'll notice these t's here cancel in the denominator. I get the same formula we had before above, which is the general formula for coming up with an equation for the slope of the tangent line, anywhere on the graph. So here my slope of the tangent line will look like this. And the slope will be a little bit steeper than it was before it was in this diagram. So I need to figure out what s sub t and what s sub t plus h is. When I plug in my second t value, I plug in t plus h. So that means I replace all my t's with t plus h's. Now we need to FOIL this again. When I FOIL this, I get t squared plus 2ht plus h squared minus 1. When I plug in t, I just get my formula back out. This was given to me in the very beginning. So now I'm going to come up with a general equation of the tangent line. Well, this is the limit. This t as h goes to 0. Now my second t is the stuff I had to FOIL all out. This is what happens when I plug in t plus h. Minus my first t is when I plug in t. Notice I put that in parentheses because I need to subtract the whole thing. And I can't plug in 0 for h because it would give me a 0 in the denominator. So I simplify and hope that in the end I can. Well, when I distribute this negative sign into the parentheses, so I have to subtract the whole thing, I'll be able to cancel some of this stuff. There's a minus t squared, and that becomes a plus 1. A lot of folks miss the plus 1. But here at the end, when we start adding things and canceling, you'll notice that t squared and negative t squared add to 0. Negative 1 and positive 1 add to 0. And all that's left on top is 2ht plus h squared over h. Now we still can't plug in h equals 0. But when I factor, it allows me to cancel that h on the bottom. I can factor an h out of both terms, and the h on the bottom cancels. Now if that h on the bottom doesn't cancel for you, there's some things you could have done wrong. Usually you forgot to put your initial s sub t in parentheses. Mine was t squared minus 1. If you forget to put that in parentheses, sometimes all your things won't cancel, and you won't be able to factor out an h. But once I cancel that h, I have the limit of h equals 0 of 2t plus h. But now I can plug in 0 for h, because it's not in the denominator anymore. And when I plug in 0 for h, I'm left with 2t. So what this means is the instantaneous velocity, which is also known as the slope of the tangent line. Instantaneous. Which is the same thing as the slope of the tangent line, is 2t. So you tell me where you are on the graph, and I'll tell you what the instantaneous velocity, or the slope of the tangent line is. So s of t is t squared minus 1. Slope of the tangent line is 2t. And notice at t equals 1, which is the example we began with, the slope of the tangent line is 2, which is exactly what we calculated.